Hi, this is Math 1650, and this video is over section 8.1, which we will be starting how to do a hypothesis test. And we'll be doing hypothesis tests mainly in this chapter and then a little bit in chapter 10. So let's get through some definitions and kind of set up our hypothesis first before we actually get into testing it. A hypothesis is a statement or assumption about a population parameter. A relationship among variables or relationship among variables. We will see hypothesis for mean. Standard deviation is in 8.3, but we won't be doing 8.3. Proportions, there are some for variance and higher statistics. In chapter 10, we'll see some for correlation. A hypothesis test is a statistical procedure used to evaluate the hypothesis by analyzing sample data. The null hypothesis, we'll want to see two hypotheses for every problem. The null hypothesis is a default statement that assumes no effect. Difference or relationship. Between the variables. Okay. For your null hypothesis, you will have an equation, and the sign in the equation is always the equal sign. Sign in equation is the equal sign. You always want to set the proportion equals some value, the mean equals some value, and that value is the claim value. In correlation, the null hypothesis is that there isn't correlation, and the way we state that as an equation is the linear coefficient is equal to 0. So there's always an equal sign. So examples here. All right, so null hypothesis we'll write as h sub 0 and then 2 dots, and then we write the equation. For proportion, it could be something like proportion equals 40% or proportion equals 0.4. Okay, but there's an equal sign. For the mean, we write mu equals 5.2. That's just some claim average. For standard deviation, null hypothesis is that the standard deviation equals 1.5. The null hypothesis for variance could be something like the variance equals 225. And again, for correlation, it could be something like r equals 0. Or it will be r equals 0. The HO just stands for that. That is how you say this is a null hypothesis. So you don't have to write out the whole null hypothesis wording. but you have to have an equation, and then these numbers are always the claim value. So when we do these hypothesis tests, we make an assumption. Say the null is true. So our null hypothesis we are assuming to be true. And so what we do is, after we run the tests, we make a conclusion that we are either rejecting the null and this happens if results are unlikely. Or we fail to reject. And this happens if results are likely. To happen by chance. Basically, can we get the data we have, assuming that the null is true, and just through the pure chance of getting that data? Right, and then the other assumption is, or the rejecting is, yeah, well, I guess it's a yes or no question in a sense. We reject it if we say no. There's no way we got the sample data we got through sheer chance or probability. It's too unlikely. And then the yes option to that is we are failing to reject the null because yes, it's likely we could have gotten this by chance. Kind of like if you're rolling a dice 100 times, or let's do something else. If you're flipping a coin 100 times and you get 52 heads out of 100, well, we all can assume that that's likely. That's right around 50. It's most likely true that that happened by chance. So we will assume the null idea of the probability of getting heads is 50% to be true. And we didn't get any evidence to go against that. On the contrary, if we roll 97 heads, then the proportion of heads to tails being 50%, even though we assume it to be true, we would have evidence that it's not true. Because that sample data can't happen by chance. Right? So the alternate is the statement that opposes the null hypothesis. It describes any difference in the value in the claim value or in the relationship. And there's three possible symbols within the equation for our alternate hypothesis. It'll be a less than sign, it'll be a greater than sign, or it'll be a not equal to sign. And this is a not equal to. You know, some people haven't actually seen that sign. Maybe write equal. Right, so we could say alternate hypothesis, and we'll usually either do HA or H1. I like to do H1. Could be proportion is less than 40%, or proportion is less than 0.4. The mean could be that the average is greater than 5.2. It could be, oops, every now and then I turn that 1 into 9. It could be a standard deviation is not equal to 1.5. Or the variance, oops, why did I keep doing that? Variance is not equal to 225. Or the correlation is not equal to 0, which would say there is correlation. All right. So let's get into examples on just writing these hypotheses, because that's a big part of this. All right, so the claim is less than 50% of all adults say that cloning of humans should be allowed. So we're dealing with a percentage, so we're dealing with a proportion. That's the first thing you gotta figure out is, what is your proportion or mean or standard deviation? What thing are you looking at? And you gotta look for the clues, things like percentages, averages, just whatever is in the statement that the claim is saying. And so then we can write proportion is equal to, and then the claim value is 50%, so we'll say 0.5. And then we have to look for clues on whether it's less than, more than, or equal to. So we see less than 50%, that's our alternate. So P is less than 0.5. Okay. The claim value is always going to be the same for each one of these. Again, the equal sign is always the same in the null hypothesis. And the alternate sign is the one that has one of the three, less than, greater than, not equal to. And then it's a proportion in both cases too, so these have to be the same as well. Alright, so one thing that can help, especially towards the end, is to then write what the claim is. The claim itself is your alternate hypothesis. And so if we reject the null, then we are supporting the claim. So in this case, if we reject null, we support claim. That's one possibility. The other possibility is if we fail to reject null, then we don't support claim. Okay. Because we're not giving evidence that it's less than. Alright. The mean head circumference of all 2-month-old human babies is 40 centimeters. So the mean tells us that this is for an average. And so just that we can write mean equals some value, and then we know it has to be the mean in the alternate as well. The mean circumference of all 2-month-old human babies is 40 centimeters, so that's the value, same value, 40 centimeters. Now there's nothing on here about less than or greater than, so the alternate is going to be not equal to 40. The claim here is your null. So if we reject null, then we don't support the claim. If we fail to reject null, then we support the claim. These are opposite of question 1. And the reason is it all depends on which hypothesis is the claim. And it all depends on how the question is written. So don't think that, it's definitely one way. You have to use some critical thinking, get your mind around what are they asking, how are they asking it, and what does our data state about the claim. So, okay, third one. Claim is that 30% of all federal arrests are drug related. So we're dealing with proportions. So proportions equals 0.3. And then there's nothing again about less or more. So here the proportions does not equal 0.3. And so the claim itself is a null hypothesis. Right, so what we have in the second problem is also with the third. If we reject the null, then we are not supporting the claim. Same as question 2. For the fourth one, the mean internal body temperature of healthy adults is less than 98.6 degrees. So we see the less than sign, we see the mean, so it's a mean equal to 98.6, that's your number. And then the alternate is less than, so mean is less than 98.6. And the claim is our alternate. And so if we reject the null, we are supporting the claim. So this is the same as question 1. Okay. Claim: among smokers who tried to quit by using a nicotine patch, over half of them are smoking again 1 year after treatment. Right, so half of them is telling me a proportion. So proportion is also telling me the value, 0.5. That's the percentage. Right. Sometimes these questions don't include a value, but they do in the wording. Sometimes they don't include something that's definitely going to be a proportion or mean by saying it, but somewhere in the wording there's a hint to it. So here our proportion, our null is proportion equals 0.5. The alternate is that proportion is greater than 0.5. So this is the claim. Right, so again, this is going to be same as question 1. And the last one, the mean weight of all black bears is more than 200 pounds. So mean is equal to 200 pounds. Alternate is that mean is greater than 200 pounds. And so that will be the claim. And then this also will be the same as question 1. Okay, so that is just setting up the claim. We're going to be doing a little bit more with that as we go through these problems, especially looking at how to really get to some of these problems and getting these alternate and null hypothesis figured out. Okay, so we're going to now start a example here. And what we're going to do is go through an 8-step process, not just in figuring out the hypothesis, but in evaluating the hypothesis. And some of these steps are going to be very straightforward, others are going to have a lot of detail to them. Okay. So the scenario here is a clothing retailer wants to evaluate a new advertising campaign. If a new advertising campaign has altered the proportions of customers who visit their websites after seeing ads on social media. Historically, 30% of people who see their ads on social media visit the website. After running the new campaign, the retailer surveyed 400 people who saw the ads and finds that 140 visited the website. Has the new advertising campaign changed the proportion of customers visiting the websites after seeing the ads? Use a significant level of alpha of 0.05. Alright, so we'll have 8 steps. The first step, I call it step 0. It's just a requirement check. For proportions, we have to make sure that we are looking at a binomial distribution. Right. Now we're looking at fixed independent trials. And for this, we are looking at 400 people who filled out a survey. So that is our sample size. And the fact that we can have a sample size, and we're going to assume these people are independent of each other. That will be taken care of in the sampling process. Then we need 2 options. And for this, that means that we need success or failure. In this case, success would be how many people who visited the website after seeing the ads. So x equals 140. And the opposite of that would be if they didn't visit the website. And then we need a constant probability. And historically, that is the 30%. So p equals 0.3. Basically, that constant probability is the probability that's going to be a part of your claim value. Right. Even though nobody's really making a claim here, in a sense, they're investigating something, the historical percentage here will be considered the claim value, and then we're trying to see if we have evidence against that. Right, so we can express the claim here as p is not equal to 0.3, since we are looking to see if our new advertising has changed that proportion. And if our claim is false, then the proportion will be equal to 0.3. And so what we do is we look step 1, just writing out the claim. Step 2 is looking at what happens when that claim is false. Now we create our hypothesis. The null is always going to be the equal to. And then the alternate, we can say is p is not equal to 0.3, which is our claim. Okay, so now we are looking at a couple things here. Step 4 is your significant level. We said we're at 0.05, so we are looking at a 0.05 alpha. Okay, so alpha equals 0.05. Usually that's going to be given, or if this is actual research, it's going to be determined by the researcher. And then we want to look at our test statistic. Now, one thing we have to do is we have to find p hat. p hat is our x over n, which is 140 over 400. That comes out to be about 35%. Okay. So we can see that our sample proportion is 0.35 or 35%. That's higher than the 30%, but is it high enough to say that it's not 30%? That's the question. Is it high enough, or is this just something we could have got randomly by doing a sample? Because remember, you do your sample, you're not going to get exactly 30%. You can get 31, you can get 32. Where is that borderline? That is a difference between what happens by chance and what doesn't happen by chance. And so we have to figure out the test statistic, which is, for proportions, it would be a z-score. And it's your p hat minus your claim value at the top. So 0.35 minus 0.3 or the square root. And then notice in the bottom it's p and q. So this is your claim, 0.3 times your alternate claim, 0.7 over the 400. Okay. This comes out to be, let me do it on a calculator. So square root, I'm going to start with the bottom. Square root of 0.3 times 0.7 divided by 400. And 0.05 divided by that. Answer gives me 2.18. So that is my test statistic for my z-score. Now, when we get into problems involving the mean, your test statistic could include either your z-score or your t-score. It all depends on if you know the population standard deviation. If you do know it, then it's a z-score, and it looks very similar to what we just did, but notice it includes the standard deviation, the population standard deviation in the bottom. And if you don't know the standard deviation, then it's a t-score. It includes the regular standard deviation, the sample standard deviation in the denominator. Okay. But notice it's very similar to a regular z-score, the data value minus the mean over your standard deviation with that correction. Okay, so let's keep going with this. We're going to have to now determine the p-value or critical region for our test statistic to help decide whether that test statistic is too high or too low, or just right, I guess you can say. So a couple definitions here. First, significant level, that is denoted by the 0.05. And this is the probability used to determine if the null hypothesis is rejected or not. And then its common levels include 0.05, 0.01, or 0.1, but it doesn't have to be those. Critical regions is the area in the tails of the distribution where the null hypothesis will be rejected. And then the critical values are the values that separate the critical regions from the non-rejection region. All the values that separate the critical region from the non-rejection region. And this is determined by alpha and the type of test. Okay. So we're going to go through 3 different types of tests and looking at where the critical regions fall, where the non-rejection regions fall, and what it means for the alpha. So a two-tailed test. The non-rejection region is in the center. This is very much like the confidence intervals. Non-rejection region is in the center. And then you have a negative critical value and a positive critical value that separate the two. Alright, now our rejection region then, I'm going to do in red, of these regions here. And so what this means is that if we get our test statistic in the upper rejection region, our sample value is too high to still be equal to whatever the claim value is. It's just too high. And if it falls in this lower rejection region, then the sample value is too low. So we are looking at a hypothesis where, for the coin, P equals 50%. If we test it and we get 30 heads, well, that proportion is just too low for the actual probability to be 50%. If we get 70 heads, then that proportion is just too high for the probability to still be 50%. Okay, and so we would reject the null in those regions and say that we are supporting the claim or supporting the alternate hypothesis. Okay, so critical regions or rejection regions are in 2 extreme sides, and each with an area of alpha over 2. Okay, and this is we use a two-tailed test when we have an alternate B that some proportion or some mean is not equal to. It's always the not equal to sign. Right, and so if we are using the 5% alpha, then this region here is 0.025, and this region here is 0.025. And so then the critical values will be evaluated when we're at an area to the left of 0.025, an area to the left of 0.975. It goes back to what we did in the normal distribution. Right. The left-tailed test. Let's switch colors so it doesn't blend with the top. Critical region is in the extreme left. with an area of alpha. Because the whole significant level is in that extreme far left. So this is your critical value. That's the rejection region. And this is meaning sample value is too low. Okay. And so we use this when our null hypothesis has a less than sign. Meaning we got a test statistic that is just too low. And so we can support that our actual value is less than the claim value. So this area here would be 0.05 if we are using a 5% alpha, which means that the critical value we found at the 0.05 level. The right tail test is basically the opposite of the left tail test. Critical region is in the extreme right. With an area of alpha. This is your critical value. This is your rejection region. And this means that the sample value is too high. And we use this when our alternate is greater than sign. Meaning that sample value that we got in our sample is just too high to be equal to the claim value. So it has to be greater than the claim value. Alright, so the last thing here is, it's a definition, the p-value. The probability of obtaining a test statistic at least as extreme as the one observed, assuming the null is true. Think about is it's the probability of our sample data happening, assuming the null is true. Right, and it's basically the measure of strength of our evidence. Alright. So we have a 2.18 z-score from our business example. That's what we did before with our social media advertising. Let's figure out this. Oh, hold on. Before we do that, let's go back for a second. We are looking at a two-tailed test now. Because it's a not equal to. And remember our alpha is 0.05. Right, so we're going to be using those. We have two-tailed tests, so we have two regions here. And in each of these regions, this is going to be 0.025, and this is going to be 0.025. And so we're going to do a couple things here. First, we're going to find the critical values. And so to do that, we'll go to a normal distribution. and we're going to put in the areas. So 0.025, and we get a negative 1.96, 0.975, we get the positive 1.96. And then we're going to do the area of our z-score. So we'll put in 2.18. And what we want to do is look at what's called the two-tailed percentage. And that is 0.02926. So I'll just write it as 0.029. All right. So what does this do, and what are we going to find out by this? There's two ways of looking at making this decision, and this is step 7 now. Determine a decision about the null hypothesis based on the critical region. Well, our z-score is 2.18. That falls in blue right here, just higher than this. All right, so it's in what's called our rejection region. So if test statistic falls in rejection region, we reject the null. If test statistic falls in non-rejection region, then we fail to reject the null. Our test statistic fell in the rejection region. It was just too high for that proportion of 30% to be still true. So we reject the null hypothesis. Since 2.18 is in rejection region. The proportion equaling 35% is too high for null to be true. That's a conclusion for this, but we're going to look at it a different way now. We're going to look at it based on the p-value. We reject based on the p-value when p is less than alpha. And we fail to reject when p is greater than alpha. In our case, 0.029 is less than 0.05. Okay, so we would reject null hypothesis since p-value is less than alpha. And this means that the sample portion is unlikely to occur by chance. Now, both of these methods to come to a conclusion can be used at any time. or for any problem, they will always agree. So if your critical region determines that you're rejecting, your p-value has to also make that same determination. If it's not, then you're not doing something right? So usually I focus on the p-value because for me it's easier just to look at a number and compare it to another number. But it's good to know that you can look at a graph, and when we get on StatDisk, you're going to see that you're given a graph to help see this. You can look and see where the test statistic falls. So it doesn't matter which one you decide to use. You can use both just to confirm, but they will always agree. Alright, so now we want to write, and this is the last step, write a conclusion, and we have to bring the conclusion back to the claim. We can't just say, oh, we reject the null, or we don't reject the null. We have to bring it back to the claim and determine what this means. So our conclusion for this could be written as the hypothesis test revealed evidence to reject the null hypothesis and support the claim that the advertising ads have changed the proportion of customers that viewed the website. We bring it back to the claim, we bring it back to the context of the problem. Okay, now we have a couple errors that can happen in a hypothesis test. First, the type 1 error. This occurs when H sub 0, the null hypothesis, is rejected, but it was actually true, denoted by alpha. Denoted by alpha is that type 1 error. Kind of looks at, okay, you got 5% chance of having an error here. Basically, either your alpha is maybe too big and that's why this happens, or maybe your sample size is too small. That's usually one of the two is the case. Type 2 occurs when H sub 0 is not rejected, when it is actually false. This is denoted by 1 minus alpha. Okay. One way to think about this is alpha is too big for a type 1 error, and so that's why we are rejecting it even though it's actually true. The other side is alpha is too small, and that's why we are not rejecting it. Our p-value is higher than it should, than the alpha in that case. Where if we use a bigger alpha, then we would actually reject it. Sample size can cause this issue as well. So sample size and then determination of the alpha. Now, in business, a lot of times, this is why they use a 0.05, because it's the best of these to, it's usually not too small or not too big to give a decent chance at, having a true hypothesis test and not lose money for that matter. The power of the hypothesis test. The power of a hypothesis test is the probability of supporting an alternate hypothesis that is true. And being able to reject or null and have evidence against it is the purpose, because we're usually going to have the claim be an alternate, not always, but a lot of times, because we are going to start with some historical data or something like that that would suggest that we need to or try and look for evidence against that. All right, so we're going to conduct a lot of these hypotheses on StatDisk, and a lot of it's going to be just being able to figure out what values you have and plug in the values, and then you'll get your results out. Now, you won't get the results of whether you should reject it or not. You'll get the results of where it will fall in the critical region and what your p-value is. Then you have to make that determination from that. So there is going to be some writing stuff down, maybe not as much as I have been writing, but there is some stuff you have to write down in order to use the hypothesis test on StatDisk. A lot of it's dissecting the problem first. So let's do an example using StatDisk. A tech company is testing a new software update for its mobile app. Previously, 40% of users reported experiencing bugs with the app. After the update, the company surveyed a sample of 250 users and found that 85 of them reported bugs. Has the new software update significantly reduced the proportion of users experiencing bugs? All right, so we'll look at the requirements here. Fixed number of trials. N equals 250. That's what we sampled. And each user is independent. Two possibilities. They experience bugs, and so we have x equals 85, or they don't experience bugs. Constant probability of this happening. Well, we're basing this on the 40%, so p equals 40% or 0.4. And so we can look at p hat then. It's 85 over 250. And that's 34%, which is lower than 0.4, but is it low enough? The question. All right, so we're going to now set up the hypothesis. Okay. So our claim proportion is that it's equal to 40%. And then we want to know if it's less than. We want to know if this has reduced. Not that it's different, that it's less than. So p is less than 0.4 is our alternate, which is the claim. All right, and then the significant level, it wasn't given, so we're going to do an alpha of 0.05. That's usually the best. And so now let's put in what we need to put in into the StatDisk. So to get to the hypothesis test, let's go back to the beginning. Do analysis, hypothesis testing, and since we're dealing with proportion one sample. We have to make sure we do the drop down. This is less than, so proportion is less than claim value. This is basically saying p is less than or 0.4, We have to put in 0.4 for our clean proportion. Significant level, I'm going to do this so everything's going to be seen. All right. Significant level was 0.05. Sample size was 250. Number of successes was 85. Okay. And we have everything filled out. Make sure you don't forget the alternate hypothesis because that's easy to be forgotten. But we will evaluate it. Okay. You get back your sample proportion, so 34% is what we got. That's what we get back. You get back your z-score. So in the results, C equals negative 1.94. You get your critical values. So your critical values are minus 1.645. Notice there's only a minus sign, not plus and minus. This because it's a one-tailed test. You're only going to get one critical value. And then your p-value is 0.026. Right. We're not going to worry about the confidence interval on this, just these four. Right now, we can look at a plot, but before we do that, I'm going to draw the plot. So, bell curve. Critical value, there's only one. It's a negative 1.645. We want to decide, is the test statistic in the rejection region? Our statistic is negative 1.94, so it is. Right. And so from this, we can say we will reject the null hypothesis. And then we look at our p-value. Our p-value is 0.2026, which is less than 0.05. So again, we reject the null hypothesis. Right. So on StatDist, it shows you the plot, so you don't always have to draw it. The red is our critical value, the blue is our test statistic, and it's to the left of the critical value. So this is considered too low to be the 40% be true. And so we can say in conclusion, we have evidence supporting that the new software reduces the bug issue. All right. In 8.2, we will be doing more testing on proportions, and I will see you then.